So we're back to max-min problems, everyone's favorite. And if you clicked on the link before this video, you got a quick review of how to find the surface area of a circular cylinder. I hope you're relatively familiar with how to find volume. In general, volume is area of the base, right? So the area of a circle is pi r squared. So volume in general is the area of the base times the height. And if you were to unroll this, as was shown in that video clip, the rectangular portion, right, when that unrolls, the length of that is actually the circumference of the circle, all right? And so we just reviewed, we better review these because I know not everyone knows these as well as they should. But the circumference of a circle is pi d, and area is pi r squared. And if you have trouble remembering that, a cute little saying is cherry pies delicious, apple pies are too. All right, so cherry pies delicious, apple pies are too. Now the diameter, of course, is equal to 2r. All right, so I'm going to use that when we talk about this is the circumference. I'm going to use 2 pi r so that we're all in terms of one variable r. All right, so then the area of this region is 2 pi r times h, and the area of the top and the bottom here, since they're both circles, is pi r squared, and we have 2 of them. All right, so that is how we get this formula here. So anyway, in this problem, we have a 12 fluid ounce soda can, and it's twice as thick on the top and the bottoms as it is on the sides. And we're given a volume in cubic inches. All right, so we're actually given a volume in fluid ounces and a volume in cubic inches, right? Just giving a volume in fluid ounces probably seems like it makes a lot more sense to you, right? That's what's normal. But anyway, when we go to do this problem, and we want to minimize the amount of material. So minimizing material is keyword for minimizing surface area. So we talked about the reason behind these max-min problems and how they get used in real life. And a manufacturer wants to enclose a certain amount of product, but do that using a minimum amount of packaging material. All right, so these types of problems really do have a practical everyday use. And we talked about the constraint equation, right? What is it in the problem that constrains me from making this a very, very small amount of material? You know, I want to use a minimum amount of material. Well, why can't I make this little tiny, tiny can? Well, I can't do that because I'm constrained by this certain volume. Okay, and then the objective equation is the one that I want to find the maximum or minimum of. So the objective equation is the one that I plug into my calculator, right? And then go to second, calculate, and find the min. So anyway, I'm given 2 measurements here, 2 different units of measure, right, for the volume. One's in fluid ounces, one's in cubic inches. Your instincts probably say use the fluid ounces one. That's what's, quote, normal. Right? We never talk about a volume of a soda can in cubic inches. The reason we can't take the 12 fluid ounces is because I can't measure my volume in a unit that is not consistent with what I would measure a radius and a height in, right? My equation needs to be all in the same unit. So I can't measure a radius in fluid ounces, and I can't measure a height in fluid ounces. I can, however, measure a radius and a height in inches. All right, and so that's why I need to represent volume in cubic inches so that I have the same unit throughout the problem. So I plug in for the volume, and that's what constrains me. And when you have both of your equations sitting there, right? A lot of times people will get stuck. They'll get both of their equations sitting there. They get stuck right here where they say, okay, I've got these 2 equations. What do I do with them? So what we do is we take the constraint equation and we solve it for one variable because our constraint has to work our way into our objective equation. Somehow the constraint has to come into play here. And when I go to graph this objective equation, I can't graph an equation on my calculator with two variables, right? Because on my calculator, I'm going to put x in here, and I'm going to have an extra variable. So I'm going to have to solve this for one variable, right? And the obvious choice would be h. And then, as I've said many times, if you want to be a good mathematician, you have to get good at substituting things for their equal. All right, so I'm going to be able to substitute this quantity for h. Now, there's one other little twist to this problem that we have to consider. The soda can is twice as thick on the top and bottom, right? Which means that I have this representation for the area of the top, the area of the bottom, right? The 2 pi r squared represents the area here and here, but this is twice as thick, right? Meaning that I need to double, right? I need to go from a 2 to a 4. I need to double pi r squared to represent that amount of area twice, since it's twice as thick there. So now I'm going to plug in for h. Okay, and for this specific problem, since it was twice as thick, right, I've had to change that to a 4. And it would make the most sense to get my equation all cleaned up nicely before I plug it into the calculator. Okay, you don't have to though. Honestly, if you took this equation right like this and plugged it into your calculator, that would be okay. All right, without doing any cleanup. And by cleanup, oh wait, I was replacing that with an R. I wasn't crossing those out, I was replacing them with an X, because on your calculator it will be an x. And this is pi r squared. So when I say clean up the equation, I mean combine like terms and also cancel, right? These will cancel, which I'm not supposed to say cancel, I'm supposed to say divide to 1, right? So pi divided by pi is 1. I have r over r squared, so that will simplify to just r here, and then I can multiply that and get 43.3. And sometimes the hardest part about doing this graphically is picking the window. All right, so I have to think logically about a soda can. I mean, think about what the radius of the soda can might be. We're in inches, I think, right? Yes, we are. We're in inches. Okay, and remember, it's better to pick a window that's a little bit too big. So I'm thinking that a reasonable window would be like 0 to 2, right? Because a soda can's radius is really not that big. Okay, so I'm going to plug this equation into my calculator, and I'm going to graph from 0, put in 0 to 2 for x, and then I'm going to do a zoom fit. All right, so play along with me. Get this entered in. And I don't like the way it looks like that, right? I can hardly even see where the min is. So my zoom fit gave me a way larger range of y values than I really need. So if I go back to window, my y value is actually up here at 1,700. I think I could take that y, like if I cut my window back like this, right? If I did this somehow, I bet you I could cut that y down to like 100. right? And then I would see the minimum more clearly, right? I would have more definition for that minimum so that I could go to second calculate. And that's perfect. As soon as I changed that to Y, I got a much better definition for my min, like that. So I'm going to go to second calculate. I'm going to mark off my left bound. I'm going to mark off my right bound, and I'm going to find that min. And in this problem, I only told you to find the radius. That means we get to stop as soon as I find a value for x. I don't have to plug in and find anything else. So if I rounded to the nearest tenth, it would be 1.2, and I should include inches, right? Units are important. That's my radius. I didn't tell you to find more than just the radius. If you had to find the height, you could go right back up here, right? If I told you to also find the height, you would plug in the 1.2 for the radius, compute this. You'd have to put like this part in parentheses, right? Do 21.65 divided by parentheses pi times the 1.2 squared, and that would give you the height. Okay, but I didn't make you do that. That was nice of me. So anyway, let's pause for a minute. These problems are so much work, we kind of need a break in between everyone.